Hello everyone and welcome back. My name is Mr. Kovalt, and in this video and the next several videos, I'm going to be going over molecular orbital theory. So let's get into this. So molecular orbital theory, what is it? Well, it's a delocalized approach with regard to the electrons. So when we're talking about Lewis dot structures and valence bond theory, uh, these theories don't adequately explain everything, right? So valence bond theory does explain some things well, better than say Lewis dot structures, such as shapes and things like that. But it's not perfect. There are still things it doesn't explain. So, for example, why are some compounds colored and others are not colored? Why do some substances with unpaired electrons, why are they stable and some aren't? Why are some substances effective superconductors? And also, one thing that they don't really explain very well or describe is this nature of resonance, right? We saw that resonance is this idea, or it's this concept that the bonding of different atoms in certain molecules are somewhere between a single or a double bond or a triple bond. They're not quite single, double, or triple, somewhere in between, right? We saw that with valence bond theory, where you can calculate the bond order by counting the number of atoms that are bonded and counting the number of bonds and dividing by the number of bonds by the number of atoms, and then you can kind of get an average. And so that kind of goes so far, but it's not as adequate as we need it to be. And so therefore we have molecular orbital theory comes to the fore to try to explain these things, right? So here, for these approaches like valence bond theory, or when we draw our Lewis dot structures, we're assuming that the electrons are localized. What does that mean? That means that when we pair up the electrons, we saw with valence bond theory, you have an unpaired electron on this atom in this orbital, whether it's a unhybridized orbital or a hybridized orbital. And then we have this atom with an unpaired electron in whatever orbital, and then they kind of pair up. And then those two electrons are shared directly between those two atoms and only to those atoms, right? So we have those bonds, right, that are between the two atoms. We call those the atomic orbitals, right? The atomic orbital of one atom is overlapping with the atomic orbital of another atom, and so they form a bond. And those two electrons are localized between those two atoms that are bonded together, right? So we call that a localized kind of theory. But however, molecular orbital theory, or MO theory, kind of throws that out and says, no, the electrons are delocalized, meaning that the electrons don't belong to just those two atoms, but to the whole molecule itself, right? So we see the atomic orbitals, right? We see the sp hybridized or the sp2 hybridized orbitals. Those orbitals belong only to that atom, right? So we take the atomic orbitals, the s and the p and the d, and we hybridize those. But those orbitals belong just to that atom, right? So if we're looking at the orbitals on a particular carbon atom, we take the s and the p's of that particular carbon atom, we hybridize them, we combine them, and then we get the sp hybridized or the sp2 hybridized orbitals. But those orbitals only belong to that particular carbon atom from which the atomic orbitals, the unhybridized atomic orbitals, came from, right? But in MO theory, we take the atoms, the atomic orbitals of all the atoms, and we add those together and we form molecular orbitals that belong to all atoms or the whole molecule. So we're going to get into that. So let's move on to molecular orbitals. Okay. So previously, we described electrons in isolated atoms as having certain distributions or orbitals, each with a particular orbital energy. So, for example, if you have a nitrogen atom, then you have, certain number of electrons in the nitrogen atom, right? So let's say 7 electrons. So those electrons are in different energies, different spatial arrangements. You have it in the 1s orbital, the 2s orbital, and the 2p orbital, and so you fit those in. And so those orbitals belong to the nitrogen atom. And so if that nitrogen atom is involved in bonding, let's say, then you get the hybridization of the orbitals, if need be, to be involved in bonding. But again, those orbitals are atomic, meaning that they belong to the atom. So the positions and energies of the electrons in atoms can be described in terms of atomic orbitals, or AOs, right? So atomic orbitals belong or are localized to that particular atom, or in bonding, they're localized between the two atoms that are sharing the electrons in the bond. So the positions and energies of electrons in molecules, however, can be described in terms of what are called molecular orbitals, or MOs. So a molecular orbital is going to be a particular spatial distribution of electrons in a molecule, right? So let me go back here. So here, when we're talking about positions and energies of electrons in atoms, right? If we're talking about it in atoms, they can be described in terms of atomic orbitals, right? Belonging only to the atom. But if we're going to talk about the position energies of electrons in molecules, that also can be described, or the electrons can be described in terms of molecular orbitals, such that, again, just like the atomic orbitals are certain spatial distributions with certain energies, then a molecular orbital is also going to be a particular spatial distribution of electrons in a molecule that is going to be associated with a particular orbital energy, right? So the difference is going to be that molecular orbitals are not localized on a single atom, but are going to extend over the entire molecule. So the electrons don't just belong to a particular atom in the molecule, they belong to the whole molecule. And so this is going to be referred to as molecular orbital theory, or MO theory for short. And this is a delocalized approach to bonding rather than a localized approach that we've dealt with before. So that is the brief introduction to molecular orbital theory. So let's go on and continue in getting into the details of this theory and how it applies in bonding. Okay, let's talk a little bit about molecular orbitals. So getting molecular orbitals is computationally demanding, right? So when we're thinking about orbitals, we're going back to wave functions, because that really is what an orbital is. The wave function it's a mathematical construct. The orbital comes from the wave function, solving the wave function. So that is going to be demanding mathematically or computationally. But the principles upon which molecular orbital theory is based are similar to what we used when we're determining the electron configurations for atoms, right? So when we do the electron configuration for atoms, right, we take an atom and we figure out, well, how many electrons are in the atom. Like, say, sodium, it has 11 electrons. And so then we fill in the electrons according to the order and energy of the orbitals, right? So we start with the 1s orbital, right, on the bottom. We go to the 2s orbital, and the next we have the 2p, and then the 3s, and then the 3p, and then the 4s, and then the 3d, and so on. We have our orbital diagram, and we take the 11 electrons and we follow the principles. We put in 2 electrons into the 1s, and then we put 2 electrons in the 2s, and then we start to put in 1 electron into the 2p orbitals one at a time, using Hund's rule, following Hund's rule, right? So we can use those same principles when we're talking about molecular orbitals. However, the key difference here is that in molecular orbitals, the electrons are allowed to interact with more than one atomic nucleus at a time. So there we're taking molecular orbitals that are basically gotten from putting together and combining atomic orbitals from different atoms. So just as with the atomic orbitals, we create an energy level diagram by listing the molecular orbitals here, not the atomic orbitals, but the molecular orbitals in order of increasing energy. And then we fill those molecular orbitals with the required number of valence electrons according to the Pauli exclusion principle, right? So we start, again, we're going to, instead of having our atomic orbitals, again, the atomic orbitals are like 1s, 2s, 2p, 3s. But instead of having atomic orbitals with s's and p's and d's and f's, we're going to have molecular orbitals, which are a combination of s's and p's and d's and things like that, right? So we're not going to call them 1s orbitals. We're going to call them something different, which we'll get into a little later. Now, because we're following these same principles, each molecular orbital is going to also hold a maximum of 2 electrons with opposite spins, right? So those principles still apply. So now let's go ahead and talk about the molecular orbitals in detail, starting with molecular orbitals that come from the s orbitals. Okay, so let's talk about molecular orbitals that only involve or that involve only the s atomic orbitals. So our simplest example would be the H2 molecule, because there we have a hydrogen atom with 2 hydrogen atoms that are going to come together and bond. Each hydrogen atom has 1 electron. That 1 electron is in the 1s orbital. So that's going to be a combination of the 2 1s orbitals to form a molecular orbital. So when we're overlapping atomic orbitals are going to be described mathematically by mathematical equations called wave functions. I mentioned this before. Wave functions are basically very complicated mathematical equations that are going to describe the probability of where to find the electron. Again, we're thinking of electrons as traveling in waves, right? So instead of thinking of it as particles, we're thinking of electrons as waves. And so that's going to influence that's going to influence how we think about when they come together and they interact. So the 1s atomic orbitals on the 2 hydrogens are going to interact to form 2 new molecular orbitals. So we have each of the atomic orbitals on the 2 hydrogen atoms, the 1s over here, 1s over here. They're going to come together. They're going to interact with each other to form 2 molecular orbitals. And so if we're thinking of the electrons as waves, then we can also think of them in terms of how they interact in the same way that waves interact, right? So if you if you bring to your mind water waves, for example, if you think about water waves, when water waves interact with each other, there's a couple of different ways they can interact. They can interact constructively, meaning that when they come together, you have peaks and peaks meeting together and troughs meeting together. And so when they meet together, they are going to interact so that way that the resulting wave is going to be much more higher, right? So for example, if I put it this way, if I have 2 waves interacting like so, right? If these 2 waves interact such that the peaks are in line with the peaks, then I'm going to get a bigger wave with larger larger peaks and lower troughs, right? So that would be constructive interference. If the waves are not aligned, right? So if they're aligned such that if I have this wave here, but then this wave is like that. You can see that the peak of this wave and the trough of this wave are meeting such that they're going to cancel each other out. Same thing here. This peak meets with this trough. That's going to cancel out. So what happens is that everything cancels out, the waves, and you don't get a wave, right? You see this in water waves, right? Where if you see two water waves coming together, you start to see parts where the waves meet such that you get larger waves, and then in between you'll see that there are places where the water is kind of smooth, there is no wave, and so that's where you get what is called destructive interference. So constructive interference is when they add together and you get a larger wave, and destructive interference is where they come together and you get a lower wave or you get no wave at all. That would be like completely destructive. So that's what happens with molecular orbitals. The formation of molecular orbitals from atomic orbitals occurs in the same way because we're thinking about electrons in terms of waves. So when the two electrons come together in their orbitals, then they're going to interact in the same way that waves interact. So you can get two different molecular orbitals from those interactions, right? So if you get construction, right, if you have a molecular orbital is from the adding of those two atomic orbitals, so atomic orbital from atom A and atomic orbital from atom B, if you add those together, you get one molecular orbital. This would be like the constructive interference. And then if the atomic orbital of atom A, if you find the difference between the atomic orbital of atom A and the atomic orbital of atom B, you're subtracting, that would be like the destructive interference. And so because you can get the constructive and destructive interference, that gives you two possible molecular orbitals from the two atomic orbitals. And so here, the molecular orbitals are created in this way here. They're created in a way that is called the linear combination of atomic orbitals, or LCAO. This is what we're talking about here, where you're getting either constructive or destructive interference. You're either adding them together, you're adding waves together, or you're subtracting them. And so, therefore, one thing that we need to keep in mind is that a molecule must have as many molecular orbitals as the atomic orbitals that are being interacting with each other. So again, this is kind of like the hybridization that we saw with valence bond theory, right? So when you hybridize orbitals, atomic orbitals on a single atom, right? You take the S's, you take the P's, right? You have one S and you have like one P or two P's or three P's, and you put them together and you get hybrid orbitals. The number of atomic orbitals that you put together to hybridize, that is going to be the same number of hybrid orbitals. So if I take an S and a P, that's three atomic orbitals. I hybridize those together as I combine those together, and I get out three equal energy sp2 hybrid orbitals. It's the same thing with molecular orbital theory. Whatever number of atomic orbitals that come together, that's the same number of molecular orbitals that I should get for the molecular orbitals, the number of molecular orbitals. Okay, so let's move on. We'll talk about this in more detail with hydrogen, and I'll show you more, explain a little bit more what we're talking about here. Okay, so let's use a picture here to help us understand what's going on with the combination of s orbitals from your hydrogens. So again, we're dealing with the simplest molecule, which is two hydrogens coming together to form a bond, to form a molecule, and what's happening in the process with the electrons and the wave functions and orbitals and things like that. So here we have our 1s orbital for one of the electrons, right? So here's the one of the electrons, the 1s orbital for one hydrogen here. This is the wave function for this one. So chi here or psi, I'm sorry. So psi here represents the wave function. So here we have the wave function of the electron in the hydrogen here. So this is our hydrogen, let's say hydrogen A. And this electron is in the 1s orbital. So here's the 1s orbital for the hydrogen. And so then for the second hydrogen, hydrogen B, it also has its wave function, right? So these are separate. So here's an atomic orbital, the 1s orbital in this hydrogen. So this electron is in the 1s orbital for this hydrogen. This electron is in the 1s orbital for this hydrogen. And these are the wave functions for the two separate hydrogens. Now, when they start to come together, right? So when they're, and in this case, we're looking at constructive interference where the atomic orbitals on the separate atoms combine constructively rather than destructively. We'll look at destructive after this one, but this one we're looking at the constructive interference. Remember, we're thinking of electrons as waves. So here's the wave functions. If they combine constructively, then the overall result is going to be an intensifying of the probability of the electron or the wave function itself. So here you see the two atoms coming together, and then you get the combination of the two wave functions of the two hydrogens. So the nuclei are closer together than they were before, so they come together. And then look at the wave function of the combined orbitals. So here we have the wave function of the resulting molecular orbital of the, or I should say the combined wave function of the electrons, right? So these two waves come together and you get the combined wave function. And you can see here now that there's a high, I should say, lack of a better word, probability of finding the electron. You can see here between the two hydrogens. Here you can see, right, so there's no wave function here, no probability. And then you get this here. And then so if you do a square of the psi squared gives you the radial probability distribution of where the electrons would be. And so in this molecular orbital here, we call the sigma 1s. So now you can see that this is the molecular orbital of those two atomic orbitals that were combined. And you can see the probability distribution of finding the electron. And now you can see that there's a high probability of finding the electron in between the two nuclei, right? So we have nuclei here, and then there's a high probability. And you can see that the molecular orbital encompasses the whole molecule, right? So it belongs to the whole molecule, not just to one atom or the other. And so there's a few things we want to say about this. So the molecular orbital corresponding to the sum of the two hydrogen 1s orbitals is called the sigma 1s. That's how you pronounce that. So this symbol is the sigma. That's a Greek symbol, sigma, and so this is called sigma 1s. So the two 1s orbitals combine to form the sigma 1s molecular orbital. So the two atomic orbitals, 1s, form the sigma 1s. And the 1s here indicates that this molecular orbital sigma is a result from the combination of the 1s. So that's where they're coming from. So that's why we call it a sigma 1s. And so the other thing I want to point out is that a sigma orbital, one of the reasons, or the reason we call it a sigma orbital, is that it is a bonding molecular orbital, and I want to highlight bonding. So bonding as opposed to anti-bonding, which we'll talk about in a moment. So the sigma orbital is a bonding molecular orbital in which the electron density is along the internuclear axis between the nuclei and has a cylindrical symmetry. What does all that mean? It means that when we call a bond sigma, it means that the electron density, right here, the the electron density, the probability density of finding the electron in between the atoms is 1 along the internuclear axis. What does that mean? It means that it is right between the two atoms, right? So if you were to draw a line directly between the two atoms, that would be the axis, the internuclear axis. And so the density is between the two nuclei. So right between the nuclei, that's called the internuclear axis. So that's where the electron density is located, right? That's part of what we mean by sigma, right? And it has a cylindrical symmetry, right? So you can kind of see that as a cylindrical symmetry. What does that mean? It means that a cylinder, it has a cylindrical shape, not maybe exactly the same as an exact cylinder, but it's cylindrical in the sense that if you were to cut it perpendicular to its axis, then you would see circles, right? So for example, this marker here has a cylindrical shape. So if I turn it this way and I start cutting it in half along the axis, perpendicular to the axis here, then along this way, then you would see circles. Look at that circular shape. So if I cut it, you'll see a circle because it's a cylindrical shape. So that's what we mean by cylindrical symmetry. And so this is what we mean when we're referring to as a sigma molecular orbital forming from two atomic orbitals by constructive interference. Well, what does it look like when we're talking about destructive interference, where they come together not constructively but destructively? Let's talk about that next. Okay, let's talk about destructive interference. So we just got done talking about how it would look when you have the two orbitals, two atomic orbitals from your two hydrogen atoms combining constructively. What if they combine destructively? Remember, we said there was two ways that waves can interact. They can interact constructively, meaning that that they are going to build each other up. They're going to construct, or they're not going to destroy each other, right? So they're going to make the interaction more intense. But here, what if they're not going to be constructive but destructive? So in the previous drawing, I had both of the wave functions were on the positive side. So we have the positive and we have the negative. So before we had both of them, both the wave functions for both of the electrons in two hydrogen atoms were positive, right? So because they're positive, when they add together, that would be a constructive combining. But what if one of them is negative? So you have a negative wave function. So in this case, you have a negative wave function combining with a positive wave function, and then that's going to be destructive because negative meeting with positive is going to destroy. And so what happens is when these guys combine, when the wave function combine, you get something like this, where the wave function now has this going through 0 here. So here it's negative, positive, and then we got this 0 intensity. And so you've got this line going through here, connecting the two. And so you get this wave function from the combination of the positive and negative atomic orbitals. And this forms what is called a sigma star or a molecular orbital. So this is called the sigma S1 star, or the sigma star 1s, right? So sigma star orbitals, we'll talk about that in a moment. And so again, if you take the wave function, or not the wave, if you take the psi value, which is the wave function, if you square the wave function, you get the probability distribution of finding the electron. And of course, if you square a negative, that becomes positive. So now you've got the probability distribution all in the positive area. And so you'll see here that the probability distribution increases here and then decreases to 0 here and then increases again to here. So you get what is called a node. You get a planar node where there is no probability of finding the electron. And that is what we refer to as a sigma star. So a sigma star orbital, this is going to be the sigma star 1s. And so that is going to be the resulting molecular orbital formed from the destructive interference of the two wave functions. So that is our second molecular orbital. Remember, we have now two molecular orbitals. So remember, when you combine two atomic orbitals, you should get two molecular orbitals. And so the first one was the sigma 1s orbital that was formed from the constructive interference of the two wave functions. And then you have the second molecular orbital from the destructive interference of the two wave functions. And so there's our two molecular orbitals. We get the sigma 1s and the sigma star 1s molecular orbitals. So just to talk about how to pronounce these things. So when there's no star, it's called sigma 1s. And then when there is a star, it's called sigma 1s star. So you put star after the 1s. So the two molecular orbitals that we form is the sigma 1s and the sigma 1s star molecular orbitals. So let's talk a little bit about the sigma 1s star. So the sigma 1s star orbital is the molecular orbital that is formed from the combination, or the difference, I should say, of the 1s orbital from hydrogen A minus the 1s orbital from hydrogen B. So here this is showing a destructive interference. So in the previous one, when we formed the sigma 1s molecular orbital, we were adding those. So there's a plus sign there. But if there's a destructive interference, then we get a negative sign. So we're subtracting the two orbitals rather than adding them together. And so what does this mean? When you subtract one atomic orbital from another, this corresponds to destructive interference between the two waves, right? The two wave functions, right? Which reduces their intensity and decreases the intermolecular, or I said internuclear electron probability density. Okay, so it reduces the intensity. That's what we see here. So we have the intensity here. We have this here, negative, positive, combining, you get a negative, you get a node here, and then you get the probability distribution being reduced to 0 here. So it's lowering the intensity when you add those together. The resulting molecular orbital is a sigma 1s star. Again, the sigma indicates that we're talking about the electron distribution along the internuclear axis. The star indicates that there is a node in the plane. So when you get a node, that refers to anti-bonding. So here we have an anti-bonding orbital. So a sigma star orbital is an anti-bonding molecular orbital. What does that mean? It means that it doesn't add to the bonding. It kind of weakens the bonding between the two atoms. So anytime you fill in electrons into atomic anti-bonding orbitals, or I should say molecular anti-bonding orbitals, that's going to reduce the bonding order, which we'll talk about in a later video. And so you get an anti-bonding orbital, and then you get a sigma 1s, which is a bonding orbital. So when you fill in the bonding orbitals with electrons, that strengthens the bond between the two atoms or the atoms in the molecule. If you fill up the anti-bonding molecular orbitals, then that's going to kind of weaken the bonds or lower the bonding order. So more about that next time. I don't want to jump too far ahead. And so that is kind of an introduction to molecular orbital theory and delocalization of electrons a little bit. So hopefully this helps kind of clarify what we mean by molecular orbitals that form. We're not done yet. I'll talk more about molecular orbital diagrams and how to get your bonding order from those diagrams in future videos. But I think that's enough for this video. So I hope this was helpful. If this was helpful, if you learned a lot from this video, then please by all means like the video, share the video, hit that like button somewhere over here. Also, do me a favor, subscribe to my channel, hit that notification bell up here somewhere. When you do that, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a particular problem or question that you need help with or a topic you would like me to cover, let me know. I would love to do that for you. Thanks for joining me and have a great day.